In this lesson, we tackle related rates problems. These are applications where we will have to differentiate most of the time with respect to t, with respect to time. I do have some steps that we can follow that will help us kind of navigate these related rates problems. So take a look at these few steps. Step one will be draw a picture and name the variables and constants. Now keep in mind, I'm no artist, but a lot of times seeing a picture helps us understand what's going on. You're going to want to use t for time and also assume that all variables are differentiable functions of time t. Step two will be write down the numerical information. So this is the information that's given to you. Write it in terms of the symbols you have chosen, all right? The variables that you have chosen and so forth. Step three, write down what you were asked to find. So remember, it's hard to answer a question if you don't understand what they're asking. So make sure you write down exactly what they're asking you to find. Usually it's a rate expressed as a derivative. Number four, write an equation that relates the variables. Sometimes you have to combine two or more equations to get a single equation that relates the variable whose rate you want to the variables whose rates you know. Okay, so this requires some work on our end. We'll walk through this together. Differentiate with respect to t. Once you do this, then you can express the rate you want in terms of the rates and variables whose values you are given. Finally, you can evaluate. Use known values to find the unknown rate, all right? So these are kind of like a skeleton, kind of like map, if you will, on how we will address our problems or approach our problems. All right, so let's go for the first example. Water runs into a conical tank at the rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Okay, first things first, let's draw a picture. Okay, I did my best to draw a partially filled conical tank. All right, so here's my tank. It is, the problem says this tank stands point down. Okay, so here's the point, and it is 5 feet. This says the base has a radius of 5 feet. And this blue here is my water, and this tank is being filled with water. And the question is, how fast is the water level rising when the water is 6 feet deep? The height of our tank is 10 feet. I have X here representing the radius of the surface of the water at time t. I have Y being the depth of the water in the tank at time t. All right, very good. All right, so I'm letting capital V represent the volume in cubic feet of the water in the tank at time t. X represents the radius in feet of the surface of the water at time t. Y represents the depth of the water in terms of feet in the tank at time t. Now we're given the rate at which the volume is changing, the volume of the tank. The water runs into a conical tank at the rate of 9 cubic feet per minute. That's given. Okay, so that's the rate at which the volume is changing with respect to time. That's given to us. We're asked to find dy dt. That is, we're asked to find the rate at which the water level, the depth of the water in the tank is changing. How fast is it rising when the water is 6 feet deep, when y is 6 feet? All right, very good. Now, what we need to do is we need to state the formula for the volume of a cone. Now, this is the formula that I know for the volume of a cone. 1/3 times pi times r squared times the height. Now, R just represents the radius that I've called x, right? So instead of r squared, I'll put x squared. Let me change that. So this is 1/3 pi x squared. And then the height that we're considering is y, right? That's what y is, the depth of the water in the tank. So instead of h, I'm going to use y. So then this is the formula, the related formula that we will be using. Now, no information is given about x. No information is given about the radius of the surface of the water. So we're going to have to eliminate x because we know nothing about x. So instead, it would be better if we wrote x in terms of y. Now we can do that by using similar triangles. Look at our diagram. We have this triangle here that I'm trying to highlight there. You see it? And then the one in yellow that I've traced in yellow. And then this larger similar triangle that I am tracing in red. So what we can do is we can say because of similar triangles, we know that x is to y what 5 is to 10. Correct, everybody? X is to y what 5 is to 10. And what we can do then is this implies that x is to y what 1 is to 2 by simplifying. And then that is to say x is equivalent to y over 2. So what I'm going to do is I'm going to replace this x variable here with y over 2. So let me do that. So let's see. This formula here turns out to be the volume is equal to 1/3 pi, and x is y over 2, and that is being squared, times y. Okay, so then this can be rewritten. The volume is equal to, let's see, 2 squared is 4, and 4 times 3 is 12. So I can write this as pi over 12, and then times y cubed. So look at this updated formula, folks, for the volume. The volume of, oops, sorry, I didn't mean to do that. The volume of the water. That's what V represents, the volume of the water in the tank at time t. All right, now that we have our formula here for the volume, what we can do is we can evaluate both sides with respect to t. So let's do that now. All right, so let me just move this up here. All right, so dv dt, I'm going to take the derivative, is equal to, pi over 12 is a constant, so we'll just leave it, times 3y squared times y prime, or dy dt. That's implicit differentiation because y is a function of t. So then dv dt is equal to, let's clean this up, this is pi over 4 y squared dy dt. Now, we know the left-hand side. We were given dv dt, right? Remember the rate at which the volume of the tank is changing was 9 cubic feet per, I'm forgetting. Let me scroll back up all the way to the top here. Oh, it's right here. 9 cubic feet per minute. Remember, that's dv dt. So we can plug that value in, and we have 9 is equal to pi over 4. Now, they want to know the rate at which the depth of the water or the water level is rising when the water is 6 feet deep. And remember, that's what y represents. So I'm going to plug in 6 for y. and then dy dt is actually what we're looking for. So all we have to do at this point is isolate dy dt. So then 9 is equal to pi over 4 times 36 dy dt. I'm continuing to isolate. Here, let me come over here, way up here like that. So then 9 is equal to pi over 4. No, excuse me. Let's see, 4 goes into 36 9 times. So let me actually erase that a little bit. There. So then we have 9 pi and then dy dt. That is to say, dy dt, I'm isolating dy dt, is equal to 1 over pi, like that. So then dy dt, this is a rate, is approximately 0.32. Wasn't that a fun question, folks? So I hope that makes sense, and that'll be our approach for each problem we look at. All right, cool deal. Let's look at a brand new question. All right, next problem. I like this one a lot. A hot air balloon rising straight up from a level field is tracked by a rangefinder 150 meters from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4, the angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? All right, let's draw a picture. All right, so here we have the balloon, and the balloon is rising. Let me actually show that. So the balloon is rising like this, like that. There's my hot air balloon. Don't make fun of my hot air balloon. Here's the rangefinder 150 meters away from the liftoff point. Here is the measure, this is the angle, theta. And theta is the angle that the rangefinder makes with the ground, okay? And theta is measured in radians. Y is the height in meters of the balloon above the ground. Okay, cool. Now for us, T will be time, but in terms of minutes, we know that because of the wording in the problem per minute. Let's keep track of what is given to us and what we need to find. All right, folks, so this is given to us, the rate at which this angle is changing with respect to time. It says right here, the angle is increasing at the rate of 0.14 radians per minute. So that's given to us. And we are asked to find dy dt. That is, how fast is this balloon rising at the moment that the angle of elevation is pi over 4. So when theta is pi over 4, what's the rate at which the balloon is rising? How fast is the balloon rising at that moment in time? Okay, so we need a formula that will relate this side y, this side, this angle theta, and this side here. Well, notice that this side y is opposite our angle theta. Notice that this side here is adjacent to our angle theta. So let's use the tangent function. So what we can say is, let me move this up here. That'll be good. Let's say tangent of theta is y over 150, like that. And so this can be rewritten if you'd like, if you prefer no fraction. Y is equal to 150 times tangent of theta. Now remember what it is we're trying to find. It's dy dt. So let's differentiate both sides with respect to t. All right. Let's move this up. So when I differentiate the left-hand side, I get dy dt is equal to, now 150 is a constant multiple, so I'm just going to write 150. Now the derivative of tangent of theta is secant squared of theta, d theta dt. Remember, theta is a function of t. There we go. All right, that was the chain rule. All right. So now what we want to do is evaluate this. They said when theta is pi over 4. So then this is equal to 150 times secant of pi over 4 squared times d theta dt. The left-hand side of this equation is dy dt. Now, we are given d theta dt, are we not? Let me scroll back up here. D theta dt, there it is. D theta dt is equal to 0.14 radians per minute. All right, so let's substitute what we have. All right, so then dy dt, which is what you and I are trying to find, is equal to 150. Now, secant of pi over 4 is just the reciprocal of cosine of pi over 4, which is root 2 over 2. When you reciprocate root 2 over 2, you get root 2. What I'm trying to say is secant of pi over 4 is the reciprocal of cosine of pi over 4. So it's the reciprocal of root 2 over 2, which is 2 over root 2. But when you rationalize, you're going to get 2 root 2 over 2, which is just root 2. Okay, so this is root 2 squared. And then don't forget that d theta dt is 0.14, right? That was given. So all of this is equal to, let's see, 150 times 2, that's 300. 300 times 0.14 is 42. Oops, sorry. Point is equal to 42. All right, got it. So let's answer the question. So this represents 42 meters per minute. This is the rate at which the balloon is rising at this moment in time. Isn't that great?